collaboration with Frank Tolman and Tibor Rakowski. But there are some other points that were developed in collaboration with my former PhD student, Ewan McCulloch, and some of my new group members, Gabriele, Srivatsa, and Oliver. Okay, so, right, sorry. How do I scroll this along?
No problems, as usual. But it was working. Oh, got it. I think it's just a Zoom thing.
Oh, it's just a Zoom thing? Oh, yes, there we go.
Yeah.
And I can point at the screen like this. Okay, yeah, all right. Okay, that just about makes sense. Okay, right, good. Okay, excellent. So, the motivation for this talk. So, basic idea is that the transport properties of materials, conductivities, diffusivities are amongst the most experimentally relevant and easily accessible properties of materials. So, it's extremely useful for us to be able to calculate these sorts of things from first principles on a computer, because that way we can more quantitatively and thoroughly make a connection between theory and experiment. So it's worth improving computational methods for deducing these sorts of properties from first principles, and thinking about whether, in fact, it's possible to be able to do this with some sort of quantitative accuracy. So, of course, the problem is that calculating these things from first principles is incredibly difficult, because encoding a complicated many-body quantum mechanical system is extremely complicated. You know, if we want to encode the whole Hilbert space of a quantum mechanics problem, we need exponential number of degrees of freedom in the number of bits, qubits in the system, for example, which is, of course, a lot, especially when you want to work in the thermodynamic limit, which is the limit that's most relevant for, you know, calculating these sorts of bulk properties. So existing methods are limited, and the existing methods that I'll talk about today or allude to today are mostly things like exact evolution. So that's where you encode your entire Hilbert space in Python as a really, really long vector, and you evolve that state using a really, really big matrix. That's what exact evolution is. But there are other fancier methods like tensor network evolutions, where you encode your state using a tensor network or matrix product state type ansatz. But both of these methods have the same sort of limitation, which is that the memory that you need in order to store your quantum mechanical state tends to increase as you evolve that state in time. Okay. And the basic idea is that, you know, if you start out with a simple state, let's say a product state, and then you evolve it with a complicated many-body Hamiltonian, that state becomes progressively more entangled and explores more and more of Hilbert space, and Hilbert space is exponentially large in the number of qubits. So as you explore further and further in time, you require more and more memory, more and more numbers in order to accurately describe the state. And a heuristic that works pretty well is that the amount of memory that you need to store a state to high epsilon fidelity precision at time t tends to increase exponentially in time. Okay, so of course, if you want to evolve your state describing your qubits or your particles to some late time, you're going to need a lot of memory. Okay, so that's the issue. And I can maybe like sort of, you know, we want to understand whether this is like a barrier that we'll never get across, or whether there might be other strategies for evolving states to late times. So let me just sort of pose that problem a little bit more formally. So the sort of problems we're interested in are Hamiltonians describing particles or spins, and we're interested in modeling, let's say, translation invariant Hamiltonians. And secondly, we're also interested in modeling the sorts of systems that we often see in nature, namely systems that have some form of locality baked into them. Right. So, for example, if you're trying to model some spins in a sort of paramagnetic spin chain, the interactions, okay, they're often local. It's not the case that there's a strong interaction between the first spin and the 270th millionth spin on the chain, for example. Okay, second of all, another sort of generic feature in these sorts of problems is that these systems generically tend to have relatively few conservations. Maybe you have energy conservation. That's obviously true if you're not driving the system. But there tend to only be a finite number of conserved quantities. So we're going to be focusing on systems that have just a few conserved quantities, maybe energy, maybe also charge, maybe just one of those. Another thing that we expect to be generically true in systems of this form is that they're ergodic, by which I mean these systems thermalize, or they lose memory of their initial conditions at late times. So maybe let's just say the systems come to thermal equilibrium. This is also quite a generic feature of sufficiently complicated many-body systems. Another thing that's true is that, or appears to be true, is that within this class of systems, if you're at sufficiently high temperature, energy and charge or any conserved quantities that you do have in these systems tend to diffuse. Diffusion is quite a generic transport behavior, at least at sufficiently high temperatures. If I take a superfluid or something, or helium, and I cool it down below superfluid transition, then obviously you get ballistic modes as well. But at sufficiently high temperatures, most things look diffusive. Okay, so within this whole big class of problems, the question I want to ask is, what types of what resources are we going to need in order to calculate the transport coefficient, like a diffusion constant or conductivity or whatever, to epsilon precision? So what are we going to require in order to do that? Another sort of side question, which I'll only sort of briefly allude to in this talk, is, supposing that we have a good quantum simulator, how much better might we be able to do using that quantum simulator? Although I won't talk about that too much today. Okay. All right. So what kind of classical resources do I need in order to get my diffusion constant to within some tolerance epsilon? That's the sort of question I'm asking. Okay. So let's start by asking what resources we require to get epsilon accuracy for a diffusion constant for existing methods. Okay. So it sounds like a really tall order, right? We're given this complicated many-body system. Calculating anything about it may seem impossible, because you might pessimistically think at the very first step, well, a system with an infinite number of qubits, that's already an infinite dimensional Hilbert space. What hope do we possibly have of calculating anything in the system? But actually, you can do a little bit better than that if you realize that. Well, if you use a trick that I'm about to tell you about. So one generic prediction of hydrodynamics in many-body systems is that you can estimate transport coefficients by looking at finite time behavior. So supposing I want to know what the diffusion constant is, there's a quantity, and I'll call that d. There's a quantity called d of t that you can calculate using information from finite time correlations, which approaches d at late times. So I mean, it's kind of intuitive, if I put some dye in some water or something, I don't have to wait for infinite time in order to get a good estimate of how quickly that dye is diffusing through the liquid, right? Okay, I can look at some snapshots and make an estimate. And so it turns out that there are actually some sort of universal statements that one can make about how this finite time estimate approaches d. And in fact, it approaches it like a power law. The precise power depends on precisely how many conserved quantities you have, what dimension you're in. But in a one-dimensional system with charge and energy conservation, it actually approaches like some order one constant over square root t. The order one constant is just some order one combination of the scales that appear in the Hamiltonian. So it's like the couplings that occur in the Hamiltonian. Okay. So actually, this is pretty, and incidentally, you can obtain this formula by just truncating the Kubo formula finite time. That's what I mean by d of t, for those of you who have seen Kubo formula before. Okay, so this is actually very sort of kind of trivial observation, but also useful, which is that we can actually get a good insight into transport by looking at finite time behavior, and in particular, if I could simulate time evolution in my many-body system to some time that scales like 1/epsilon² in this case, then I could guarantee that the distance between d of t and d is less than epsilon, right? So you can get an epsilon accurate. So provided you could do the time evolution exactly for a time that scales like some inverse power of epsilon, you could actually get a really good estimate for diffusion constant. Yes.
Of course, the relevant time scale on that approximation being true is being beyond some correlation time. So your D has this normal fluctuation form. If your time is many times some correlation time.
Yeah. Well.
Yeah.
So I haven't said anything about C.
Yeah.
Yeah. So you could well engineer a system that, for example, takes a really long time to realize that it's diffusing. So let's say there's a dilute system and
most liquids are like that.
Sure.
Okay.
But I guess what I'm saying is that C that appears in my formula there is not something that's going to increase with system size.
Okay.
Yeah. Okay. In the class of problems that we're talking about, I don't want to talk about glasses or anything like that. I think I put enough. No, sure. Okay. All right. So this is already quite useful because it tells us that to get just a good with an absolute error estimate about diffusion constant, we only have to go to some time that scales like an inverse polynomial epsilon. Okay. All right. So so that means that we just have to do some finite time evolution to some time that grows like 1/epsilon², or more generally some polynomial in epsilon inverse. But I said on the previous slide that you can actually do such exact time evolutions of many-body quantum systems to finite time, but the amount of memory and the amount of computational time, like CPU time, that you need in order to do that scales exponentially in time. So if you want this epsilon accurate estimate of your diffusion constant in your classical simulation of this quantum system, you're going to need an amount of memory that scales like e to the 1/epsilon². And maybe it takes a time that scales like order e to the 1/epsilon², which is bad because if epsilon's 0.1 or something and c is order 1, it's e to 100, which is not good. Okay. So it's worth trying to improve this sort of thing. I can give you another intuition as to kind of what's going on. If we go and look at this actual formula for d of t. So d of t is this finite time truncated version of the standard formula for diffusion constant. Basically an integrated autocorrelation function for some current operators in the system. And one thing you notice is that you could obtain this formula if you knew something about the structure of J of t. Because then if you had an exact formula for J of t, you could just plot J of t into this expectation value. The expectation value is actually relatively easy to do for a sufficiently high temperature state, and you get the answer. So the point is that this J of t, as you evolve it in time, it starts off as a very simple operator and then sort of grows ballistically and becomes more complicated. And each of the components of this J of t operator end up growing in some light cone, but they become an exponentially complicated operator in that light cone. If you think about the total number of operators that you could have in a light cone, so the size of that light cone scales like t, so the number of sites in that light cone is like t. What are the number of operators in some region of size t? Well, on each site, I could have no operator. I could have, I don't know, sigma x, sigma y, or sigma z. So on each site, I have like a number of options. So it's a number that scales exponentially in t. So the amount of memory, so that's another way of seeing that, the amount of memory that you need in order to capture this kind of calculation grows exponentially in time. Okay, so that's, let's say, the existing state of the art. And so the question I'm going to be talking about in this talk is, whether we can do any better than this, and we think we can, or we have an algorithm that does seem to do better than this as well. And I'll tell you a little bit about the theory behind it. So we're going to strip the problem down to its absolute barest, most easy to calculate essentials, and just take a system that has a single conserved quantity. So suppose you have a system which has a bunch of spin half degrees of freedom on a lattice. and we have in mind some local time evolution. So that's time evolution with a local Hamiltonian or local unitary circuit, for those of you who do quantum information, that kind of thing. But just imagine that it has a single conserved quantity, the total Z components. And we're going to be trying to calculate, for some time evolution, we're going to calculate the diffusion of the Z component of this mechanism.
But not energy.
Not the energy. The Z correlations have a slightly simpler structure, but we think that they also tell us what happens in the energy conserved calculation. Okay. Right. So the raw ingredients for this diffusion constant are correlation functions. Right. So you can calculate the correlation functions if you know all of the correlation functions between these sigma z's at different times and different positions. Okay. We're going to look at these correlation functions at really high temperature. In fact, we're going to go to infinite temperature because it makes life even simpler. But it appears that our method also works at lower temperatures. It gets worse and worse as you go to lower and lower temperatures, but it also works at finite temperatures. So the sorts of correlation functions we're going to be looking at are in this so-called infinite temperature ensemble. Okay. And so notice that this, oh, whoops, sorry, my bad. Okay, we're on the punchline. Notice that this correlation function is also a kind of inner product between two operators. It's like Hilbert-Schmidt inner product. That'll be important in a second. Okay, so the reason that I've done this is because it'll allow me to sort of motivate on it. So the point is that this correlation function, from which we can calculate all of the diffusion constants and transport coefficients and whatnot, is really of the form of a quantum mechanical transition amplitude, but on the space of operators, right? So the story here is you start with some operator sigma zr, you time evolve it in the Heisenberg picture for time t, and then you take its inner product with sigma z at site 0. So if you think about that, you've taken some operator, you've hit it with a unitary linear operator, and then you've calculated its output on another operator. And so actually, this is a transition amplitude on the space of operators. Okay. All right, that's a kind of useful perspective, because as soon as we have a quantum mechanics problem and we phrase it as a transition amplitude, we can start talking about like a Feynman path integral, where at every step we insert a complete set of states. And so, at every time step, we go from one operator, and then our operator changes into a different operator, and we sum over all the different paths that our operators can take. And we get pictures that look like these. So, in this first picture, sigma z at r wiggles around. The vertical direction here is space. So here our sigma z kind of wiggles around a little bit, starts at site r and ends up at site 0. And in the second picture, sigma z r wiggles around a little bit. And then moves along and then splits into a sigma x and a sigma y. Those move around for a little bit, they recoalesce into a sigma z, go to site 0. So it's sort of space on the vertical axis, time on the x-axis here. Okay, sorry. Here's a more complicated amplitude where sigma z splits into more things. Okay. All right. So the intuition behind this method I'm proposing is the following. What we're going to do is we're going to calculate these transition amplitudes, but we're going to throw away some of the more complicated Feynman amplitudes. So we're going to look at these Feynman amplitudes, and if at some point there ends up being a lot of operators or a really complicated operator, we're just going to throw that amplitude away. And I'll tell you what complicated means in a second. But the idea is that we're going to throw away the complicated amplitudes, bound what contribution those complicated amplitudes do. Give to our diffusion constant. We'll see that actually we don't end up affecting our diffusion constant very much by throwing away these complicated amplitudes, but we do end up saving a heck of a lot of memory and making the computational procedure a lot faster. There's a trade-off that we end up with in this case. All right. So yeah, so the idea is that you look at these Feynman amplitudes and you throw away those processes which at some point involve operators that have more than, I call it L star Pauli matrices. Okay, so for example, let's say I set L star to be 2. Okay, and I decide to throw away all Feynman amplitudes that have more than 2 Pauli matrices at some point. So the first two amplitudes here are going to survive because this guy only involves one Pauli matrix at any point. This one only involves a maximum of 2. Yeah. But this one involves 1, 2, 3, 4, 5. So we throw away that particular contribution to our correlation function. Okay. And so the algorithm works by doing the time evolution and just throwing away these sorts of paths. And by doing that, we save a bit of memory, but also don't incur too much error. And what I'll talk about today is our proposed theory for what the error is as a function of this thing that I'm calling L star.
There's no obvious small parameter here. What is it?
1 over L star.
Okay.
Because if L star is infinity, then I'm not throwing away anything.
Okay.
Sorry, if one over L star is 0.
Yeah, but it's not obvious that I guess you show us how the diagrams with larger L are smaller.
Yes.
Ah,
Yes.
okay.
Yeah. I still need to explain why it is the larger diagram.
Okay.
Yeah, so in fact, our conjecture, and so we have various semi-analytical and numerical justifications for this, is that throwing away processes where they're more than L star operators incurs an exponentially small in L star error in the correlation function. Okay. All right, so just assume that that's true for a second, and let's ask now, okay, using our method, what kind of resources are we going to need in order to get an epsilon accurate approximation to the diffusion constant? So, well, first of all, I want e to the minus L star to be smaller than epsilon. Okay. So that means that I need to set L star to be larger than log of 1 over epsilon, which is not too onerous. It's actually not so hard to throw away L star. It's like 10, for example. So pretty good. But what kind of saving do we make from doing this? And the point is that if we just restrict our dynamics to this space where operators are no longer than L star, there are far fewer operators that we have to deal with. We're dealing with a much smaller Hilbert space, which means we can get away with using much less memory. Okay, so I'll be a bit more quantitative about that. So let's go back to this picture where we have an operator spreading in a line cone. So in this original picture, we just do Heisenberg time evolution on O. It spreads into some line cone that's of size order T. And as I was saying before, the amount of memory you need to sort of encode this time evolved operator scales exponentially. Okay. Now, let's suppose that instead of doing that, I threw away all operators that were longer than L star. How much memory would I need in order to encode the time evolved operator now? And it's much less. Because, so first of all, the operator is still going to spread within the light cone, because we still have locality. So it's still in this region of size order T. However, we're only allowed L star non-trivial Paulis at most. So think about how many operators are there in this light cone that have at most L star Pauli matrices. Well, the way you do that is you go to your light cone and you pick L star sites. So it'll be size of light cone, choose L star. And then on each of those sites, you could either have the identity operator or X or Y or Z. And this correctly enumerates all operators that are less than or equal to L star in size of light cone. Okay, and that number ends up looking like this: 4 to the L star, 2bt over L star. And that's something that scales not exponentially in T, scales like a polynomial in T, but a polynomial with a power that scales like L star. Okay. All right, so there's less memory required. So if you put together first of all, our requirement that, okay, we only need to really go to this time that scales like 1 over epsilon squared. And we need L star to be order log epsilon, log 1 over epsilon. If you put these two estimates together and ask, well, how much memory do we need? So you set T to be order 1 over epsilon squared, and you set L star to be log 1 over epsilon. You put those two things together, you get something that looks like epsilon to the log epsilon, which looks like e to the log epsilon inverse squared. Okay, because you have like epsilon to the epsilon. Yeah, okay, good. So the amount of memory that you need is going like this. So log of epsilon inverse all squared is better than 1 over epsilon squared. So that's why we think our algorithm sort of does better. Okay, But there's a lot. I've given you. There was a big assumption here, which is namely that this error is exponentially suppressed in L star, and I'll mainly spend the rest of the talk saying why we think that's true. But there are no proofs. There's only somewhat controlled approximate calculations and various limits, and some numerical evidence. Any questions about this so far? Yes.
Because you look like you're about to launch into explaining why that is the case.
Yeah.
Is there an intuitive way of understanding it before you? Yeah. No is valid answer.
Sort of. Although I'm kind of going to do that. In fact, like maybe I'm hyping up my proposed explanation a bit too much. A lot of it is just like an intuitive explanation, supported by some random circuit calculations and some limits, and then supported by numericals as well. So yeah, really I'll mainly be putting across the intuition. Yeah.
So you'll be, is it correct to say that you will choose to sum the series of certain diagrams? Okay, it's not that you're doing like perturbation theory in that sense. You're choosing which things to resum.
Yeah, so I
For
guess
example,
maybe a way of saying it is like there's a ton of diagrams, and I'm kind of imposing a hierarchy in those diagrams on the basis of how many and how extreme an excursion they take into the space of complicated objects.
Yeah, but
I'm
you have
controlling
something which is many bubbles,
Yes.
you add it all up.
Yeah, add it all up. Yeah. And the key thing is that the bubbles, the individual bubbles, are going to be small. Yeah. All right. So just to sort of summarize what we're sort of doing here, the idea is that we're modifying time evolution by throwing away these complicated operators. So we're evolving operators in time using Heisenberg picture, throwing away complicated paths, and in doing so, saving a lot of memory and hopefully not incurring too much error. And the result of this is that the sort of scaling with the target precision is better for our model. Better for our method. So older methods are e to the poly amount of memory required, poly epsilon inverse amount of error required. Ours is e to the some poly log epsilon inverse. Out of interest, you might wonder, if you had a ACE quantum simulator, what kind of resources would you need? Like how many experimental runs you need to do. So of course, if you could get around the decoherence problem, then you could do significantly better in an analog quantum simulator, for example. Maybe get away with poly epsilon inverse rather than having any exponents around. But of course, all of that is limited by the amount of decoherence you can have in the system. And I think an interesting, so there are various claims of quantum supremacy, for example, in analog quantum simulations of many body systems. In fact, yeah, something that we're using this algorithm to do is well, it's kind of a playful thing to attempt to do is to kind of debunk those claims. We think actually even analog quantum simulators are not outperforming our method. So yeah, it's a good challenge to experimenters to maybe control decoherence to the extent where a specialized analog simulator can do better than our classical method. Okay. All right. So, all right. So, idea is we throw away these complicated processes, and now we need to sort of explain why it is we think that throwing away these complicated processes leads to exponentially small errors. Okay. So, as I was saying, like one of the consequences for, the sort of physical picture that we're putting across is that there's a ton of diagrams, a ton of Feynman histories for the operator, which involve different sorts of excursions out of the space of slow operators. And the idea is that each of these gray boxes denotes a set of histories where the operator becomes longer and complicated, or longer, more complicated, or longer than L star. And essentially, the diagrammatic series is going to be organized according to how many of these boxes and how big the boxes are, right? Or by which I mean how long your operator gets. Okay. So, obvious first thing to try and calculate is box.
So
yes.
Maybe I misunderstood. So is it how long it is, or how many non-identity powers it has?
It's so the length of an operator for us is the number of non-identity values. I guess I should really say weight, The reason I don't like saying weight is because there's also a kind of, there's another weight in this problem. But yeah, when I say length, I mean weight for people who are quantum information. Okay, so first thing we want to calculate is just one of these boxes. And one of these boxes is a process where you have a small operator, it gets large, then it gets small again. So we want to look at these return amplitudes for operator going from being small to large to small. Okay. So it's that quantity I'm going to focus on. But provided the diagram is exponentially suppressed, provided these boxes are exponentially suppressed in L star and also suppressed in the temporal duration of the box, then this series is well behaved. Because we'll know that each of the boxes is suppressed and there's basically a geometric series associated with each of the boxes. And we'll also know that the boxes won't want to get too long, so they'll sort of remain short and we'll be able to use some the series. So the main thing to focus on then is just understanding why these boxes are suppressed, why a single box is suppressed. Okay. All right, I should say a little bit something about actually how we implement the algorithm. Something I sort of hid under the carpet or swept under the carpet was that our algorithm uses TBD as a backbone. So what I mean by that is we encode our operator using the so-called tensor product state, which is an efficient way of encoding states that have a bounded amount of entanglement, or operators that have a bounded amount of operator entanglement. And so what we do is we do a bunch of, we encode our operator as an MPO, matrix product state for an operator. We evolve it in time a little bit. Then we project onto the space of short operators. Then we evolve it in time a little bit more. Then we project again into the space of short operators. So we just periodically project back into the space of short operators. And we find that when we include these projections, the amount of memory that we need to encode the operator reduces significantly. Okay, so that's actually how we do it, for those of you who are aware of tensor network methods. I'm going to kind of skip over this bit because it's not so important. So what I mainly want to focus on is understanding why these boxes are small. Okay, so again, boxes, you start with the short operator, let's say it's on position Y. It gets larger over some course of time and becomes larger, or as large as some size L. So by which I mean it involves at least L Pauli matrices. Then becomes small again. And so the point is, I want to understand why this box is small. Okay. Yeah. No? Okay. So all right. Good. All right. So one thing that we can prove, kind of modest thing, I guess it's a good place to start, is that if you look at such an operator amplitude in a random circuit system, by which I mean a system where you lay down local Haar random gates. So it's the most random time evolution you can imagine. So if I say quantum circuit, can you nod if you know what a quantum circuit is? Okay, some people know what that is. So just trying to think of what level to explain this at, because I need half of this. So, okay. Imagine taking a look, consider at once all possible local time evolutions. So imagine a local Hamiltonian that from time to time varies in a random way, but remains local. Calculate this return amplitude for that particular Hamiltonian, square it, then average over that whole class of local time evolutions. Okay, now, provided what happens on average is what happens typically, you have a pretty good idea as to what happens typically. Okay. The point is that we can solve that average problem much more easily, often analytically. Okay. So what I'm saying is that the average over this whole class of models that I'm interested in, we can show that this return amplitude is small in the way that's required. Okay. All right. And I'll give you some intuition for that in a second. So we can actually just prove it on average. So what I mean by that is we look at gamma L, we square it, we average over all circuits, we can map that onto an analytically solvable calculation. I'm not going to go through that calculation in detail, but I'm going to give you the intuition for how it works. The next slide. Okay, and so one of the consequences for this, which I'm not really going to go into, is that you can go from showing that one of these boxes is small to showing that the correction to a correlation function is small. Okay. You can show, or also demonstrate this mirror. Okay, so let me focus on, so just focus on the top half. This slide got a bit busy. Let's just focus on the top right-hand side of this slide. So we're gonna, I'm gonna give you the intuition for how this random circuit calculation works. And so to do that, let's just rewrite this gray box in a slightly different way. So we start out with Zy. Zy propagates to some operator that has length L. That length L operator then propagates to a small operator, Zy prime. So one thing that we can do is insert a complete set of states at this point and write the amplitude for this process as a sort of summed product of these amplitudes. Okay, so that's what this expression is here. So the CZ to sigma mu, that's the amplitude for Zy to go to sigma mu, which is some string of Pauli matrices which has L Pauli non-trivial Paulis in it. And the C sigma mu to Zy prime is the amplitude for you to go to sigma mu to Zy prime. Okay, so let's rewrite this thing exactly in this way. Okay. All right, so I've rewritten it here, but I've dropped a bunch of indices just to make it conceptually a bit cleaner. So just imagine going from a Z to a sigma mu to a Z. What this is. Okay. So now the point is that in a complicated many-body system, and this is true exactly in a this is exactly true in a random circuit system, but it's also something that we expect to hold at least approximately, in some limit for sufficiently complicated many-body systems, is that these C's are like really chaotic. They have like random signs. They're really complicated objects. CZ mu is the coefficient of some string of Pauli matrices on a time-evolved operator. It's not something that we expect to sort of behave smoothly. It's likely to be very small. It's likely to oscillate a lot. We expect it to have something like a random sign. Again, this is something that's exactly true in a random circuit system. I'm trying to say that something like this is true more generally. All right. So actually, on average, we might expect this thing to disappear because it's equally likely to be positive or negative. So let's look at its square if we're going to be talking about its average properties. Okay, so we're looking at gamma squared. So now we have a sum over, we just doubled this expression, but we now need two dummy variables in our sum, mu and mu prime. Okay. All right. So now the point is that when mu is not equal to mu prime, there's no reason for the signs of these C's to be correlated. And so these sums tend to be dominated by the diagonal of the sum. You might have seen a similar calculation to this, like, if you're trying to prove that the, well, just something like the law of large numbers, or just the fact that a random walk goes like, the variance of a random walk goes like n. You'd end up getting a sum of independent binary variables. You'd square that sum, and you'd see that on average, the off-diagonal terms disappear, but the diagonal ones survive, and you only get n of those. Yeah, something a bit like that is happening here. Okay, so this is exactly true again in our random circuit calculation. It's something that we think is more true, is at least partially true more generally, is that mu and mu prime are locked to one another within the sum for the same reasons. Okay, so this sum is like dominated by the cases where mu is equal to mu prime. Okay, so now there's a useful relation that I should have mentioned before, but which I'm going to mention now, which is that there's actually a sum rule for these CZ to mu things. So, and it's this, which is basically a statement that probability is conserved under unitary time evolution. So really think about the CZ mu as being like the wave function of the time evolved operator. That wave function's norm has to be preserved. So actually there's a sum rule of this. And if you're restricting yourself to mu's which are of length L, then, well, that sum rule becomes an upper bound. Because you're just summing over a subset of all of these. Okay, so that's useful because when you look at this sum, you can pull out the largest CZ mu, or you can set, this thing to be whatever the largest one is, and then you're just left with a sum over the squares of these things. So you can pull out the largest, the largest CZ mu in this case. And we know that this first term over here is bounded above by 1. And the second term here is, well, whatever the largest one of these operator spreading coefficients is. And that's something that we can calculate exactly in the random circuit case. And it's something that we expect to be quite small. And I'll explain why we think it's small. Okay, so we have an upper bound for this gamma squared thing, and it's basically the largest of these CZ mu's. And the intuition here is that you take your Z operator, you evolve it in time, and it becomes some complicated string of operators in the light cone. And so there's a sum of many of these things, exponentially many in time, in fact. And because you see the time actually has to be longer than L in order for the operator to evolve into an operator of length L. So there are actually exponentially many in L of these C's as well. So at least on average, we know that the average size of these things is exponentially small in L. Okay. So as long as these C's are like fairly uniform, we know that actually they tend to be exponentially small in L. Now, there are a number of suppositions here and like what ifs. Like we can just prove this exactly in the random circuit case, but this is the intuition for why this holds. So there's sort of two important components here, and this maybe comes back to Elias's question. There were like two important steps here. The first step was this fact that the phases of the C's are uncorrelated with one another. So they look kind of random. And the second important thing that we used here, actually there are three important. Second important thing was that the C's have a sum rule that comes from unitarity. The third important thing is that, sorry. The third important thing is that, the likelihood of a time-evolved operator being on any particular string is likely to be quite small. Any particular long, complicated string is likely to be exponentially small in the size of that string. And those three things combined together give us this desired result. But there are all sorts of problems with this calculation. So the random circuit calculation in particular throws away an ingredient that is likely important in this problem, namely the existence of a conserved quantity. And in fact, there is a little bit more, there is certainly more structure to these CZ mu's than just looking like random uncorrelated numbers. And so I'll explain a little bit what the complications are, why we don't think so.
So is there a temperature dependence of this? Right? So now the way to prove things now, that's all engagement temperature. So that should
I haven't even made any in this part where we're talking about gamma, it's not even a statement that's made with reference to an ensemble. It's just a statement about the structure of a time-evolved operator. So there's no reference to temperature here. What temperature tends to do is it kind of like it reweights the importance of different types of strings. So for example, if you're at really low temperature, it turns out that even though there's a really small coefficient on a really large string, that small coefficient is kind of blown up by the ensemble. But I'm not really going to talk about that today. So, but that's something that's underway at the moment. I'm trying to figure that out. Okay. Okay. Yeah. Okay. So that's basically just a summary of what I just said. Okay. All right. So let me talk about some of the problems and some of our partially successful attempts to address these problems. So perhaps the most dramatic assumption here was this diagonal assumption. We just assumed willy-nilly that the mu's and mu primes are, their phases are uncorrelated. Again, that's exactly true in the random circuit system, but more generally not true. And in particular, it's not true in systems that have conservation laws, systems that we're interested in. So what we tried to do next is the next most sophisticated thing, which is to look at a system that's as random as possible, subject to the constraint that it has a conservation. So, for example, I spoke about averaging over this class of Hamiltonian evolutions, local Hamiltonian evolutions. I was saying one thing you could do is just average over all of them, and that's essentially what we're doing to get our random circuit answer. One thing you could do is put a constraint on that space and average over all Hamiltonians that are U1 symmetric, but local. So that's what we tried to do next. Try to maintain this SZ conservation and see what happens. So slightly weaker version of the same result actually continues to hold. So here it's kind of useful for us to, instead of talking about sigma Z, sigma X, sigma Y, talk about sigma Z, sigma plus and sigma minus, where sigma plus is sigma X plus I, sigma Y, sigma minus is the conjugate of that. I'll explain why in a second.
But charge density is that.
Yes, that's right. Yeah, thanks. Good. So I can just tell you what sort of happens at this point. So when you look at the circuit average of this gamma squared thing, you end up finding that mu and mu prime have to be sort of similar in that they have to have sigma pluses and sigma minuses at the same spatial locations, but otherwise they can differ by products of this local conserved density. I'll give an example in a second. So for example, if mu was this string where you had a sigma plus on side 1 and a sigma minus on side 9, the following term would actually survive. If you had mu primes having z's in different places, but sigma plus and sigma minus in the same place, this term could actually survive the circuit averaging. Whereas, I should have given a different example. Whereas, if my mu prime had a sigma minus on site 30, it would not survive. So there's a certain amount of blocking. Mu and mu prime, a part of mu has to, there are parts of mu and mu prime that have to agree, but they can differ by products of local densities. But it turns out that with some work, and there are some uncontrolled assumptions in this part of the argument, at least when we attempt to make it as an analytical argument, but the reasonable assumptions that we've got some evidence for, the same kind of argument goes through. That basically the sum sufficiently collapses that we can use the same old trick. Okay.
But just,
Yeah.
let me just check. So for each given mu, you still have exponentially many mu prime
Yes.
that will enter your sum.
Yes, that's correct. It's still exponentially many in the size of the light cone, but it's still enough because the C's are also still small and also need to be exponentially suppressed in the size of the light cone. So if you allow yourself to make certain assumptions about the uniformity of these C's, you still end up getting suppression.
Yeah, but that was my next question.
Yeah.
So what can you say about the smallness of the C's now?
Not much exactly. We still say that we have the sum rule. Sorry, this is not on the screen.
Yeah.
So we still know what their average value is within the light cone. But other than that, we have to make assumptions. If you make a strong assumption like they're all roughly the same size, which is not generally true, but if you do something like that, you go through the same argument and you'll see that this thing is still small.
So perhaps what you can say is that there will still be exponentially many terms that are approximately of the same size, which is those contain identity and z, for example. So that this would lead to something that is still exponentially decaying.
Yeah, we have a version of this in the paper. I'm not sure I'll be able to reproduce it now,
Okay.
but it's not very satisfactory though. It would be good if you have any ideas, need to say that. Okay, so there are a bunch of predictions that come out of this. So as soon as you have that this box is small, we can make predictions about the deviations that you end up getting in correlation functions. So what I've done here is I've looked at a correlation function exactly, and I'm subtracting from it the correlation function that you get if you use our method, which we call Dowling, by the way. So a prediction that comes from this calculus is that such differences end up being exponentially small in L, or L star, I should really say. And they're also attended by a certain power rule, which is something that we can predict as well and check numerically. So in this particular case, where it's this particular space-time correlation function at late times, we expect this thing to decay as t to the minus half, which is actually how you expect the original correlation function to decay. Times some power that's exponentially smaller now. Pretty good evidence that actually holds to guarantee circuits. It turns out actually that the time dependence depends on whether or not you have noise in the system. And so that's another sort of interesting wrinkle that also comes out as a prediction from what we do. So I should also say that we delved a little bit more into the U1 random unitary circuit case, and it turns out that you can map the U1 random circuit calculation to something that looks almost like a stat-mech model. And that stat-mech model, you can basically write down Feynman diagrams, a restricted set of Feynman diagrams in that stat-mech model. And so another thing that we did in our paper is we summed up a set of those Feynman diagrams that we could make sense of. And that also showed kind of non-trivially that the corrections were exponentially expressed in L. But we didn't sum up all diagrams, so that could also be wrong. Could also be an incomplete story. Oh wait, I did that. Okay, but I'm not gonna talk about that. It's kind of detailed. One thing that we can do though is simulate this model efficiently on a computer, the stat-mech model efficiently on a computer. And so I'll talk very briefly about some of those results. Okay, so I'm gonna have to speed up slightly. I don't know why I went a bit slow today. All right. Okay. Let me just go through the data and explain what's happening. Okay. So here are some simulations of some spin chain Hamiltonians. These two spin chain Hamiltonians are known to satisfy the constraints I stated initially, namely they're like ergodic and they have only one or two conservation laws and they're local. They're things that we can put on do a matrix product state calculation for. Okay, so it's hard to do any numerics in this case because, well, sorry, it's hard to do numerics without our dissipation method in this case for the reasons that I stated on the first slide. It's really hard to do exact time evolution beyond about 10 interaction times using TBD reliably, particularly if you're looking for this kind of small effect. So of course the data are kind of noisy, but they do at least broadly follow what we predict. So what we've looked at here is just the effect of a single dissipation event. So what we wanted to understand is what is the effect of looking at the time evolution and halfway through the time evolution, throwing away all operators that are longer than L star. What is the size of that contribution? In other words, that's one of the things we're throwing away. How big is it as a function of L star? And it's just a slightly simpler, cleaner, and easier to calculate quantity. So we do like the exact time evolution for time t. We throw away operators that are longer than L star. We continue the time evolution for time t. This will give us this is precisely the contribution that we would throw away if we used our algorithm halfway through the time evolution. Okay, all right. So the different colors here indicate different values of L star. And basically, as L star increases, the curves go down. And if you look at the maximum value on these curves as a function of time, the maximum contribution due to throwing away these longer operators, you find that it ends up decaying quickly with L star. Sufficiently quickly that we'd say that this is consistent with exponential decay, but of course, very hard. With only a single decade of L star, we can't ever make that statement exactly. We find it's also true in the second case, although curiously the decay is a lot slower in this case, probably because you have energy and charge conservation in this case. Okay, so that's not exactly what we wanted to calculate. We wanted, yes.
I didn't understand what that quantity is. So
yes,
because from the plot, I would understand it's something like you go to time t and then you force the operator to be longer than L
yes,
star.
yes.
And that's what you're doing.
Yes, yes.
Oh, sorry.
Yes.
Thank you.
That's
Sorry.
And that's also the size of what you would throw away
Yeah, correct.
if you threw away long operators halfway through the time.
So essentially, this P is a projector on all operators that are
Longer than our stars. Yeah. So it's not exactly the diffusion constant, partly because there's no partly because every time you apply one of this long projector is quite costly from a sort of the getting numerics. Also, it's just I don't know, slightly accidental reasons we end up focusing on this quantity. It's like a single gray box. So we want to understand the behavior of a single gray box. So you had a question.
Well, just, I think you did answer, but is it, so just make sure, so it's correct that you evolve up to the middle, that you throw away everything.
Yes.
So this, and then do you evolve the rest? Or basically,
You evolve exactly.
Yes, you take an end product. And
Yes,
just
yeah.
find a way.
Yeah, so I should have I skipped over that slide to save time, but I realized I probably should not have done that. So okay, here is an approximation to this correlation function, where halfway through the time evolution, I said, you know what, the operator is getting too long. I want to save a bit of memory. Let's project things down. The thing that I'm calculating is the difference between this and the exact thing, so I can tell how much I've thrown away.
But in your method, you're throwing away infinitely
Yes,
many.
yes. And we'll come to that. I have some data on that as well. Okay, but not deterministic data. I only have random circuit data on that. It's easier to do random circuit calculations. All right, so this is the case where we use the random unitary circuit. Okay, the data are again broadly consistent with exponential decay. Let me just highlight the second column, which is actually the difference between the diffusion constant and the diffusion constant you get by periodically projecting into short operators. So that's oh whoops, sorry. So that's okay. So that's let's focus on the second column here. And here we are more limited in L star here because to do the random circuit calculation, you have to double the system and you end up having more memory constraints and things like this. But so far as we're able to tell, we've been able to push it to larger L stars actually. But we've never seen any indication that it's anything other than exponential decay. So there's no slowing of the decay with L star. Okay, let me rush on, and then if you want, we can come back and talk about this in the question time. I should also just say that one thing that we're doing, and I last time I gave this talk, I said that the paper was imminent. Now it really is imminent. There's a hard deadline. So by the end of this month, we're hoping, well, by the end of this month, we will have a paper that benchmarks our method against some of the existing ones, so we can actually compare predictions for diffusion constants against other methods. So, of course, we have very few exact results in this sort of setting, so it's obviously hard to tell what the correct answer is, right? Because we don't really know. But we can look for clusters of agreement between the different methods and see to what extent they all tend to agree with one another and maybe learn something using that. But I guess I would say that in the cases where we do have exact results, like in certain integrable cases, our method seems to work better than others, and it's certainly like less numerically costly. So that's good. Yeah. So just to kind of advertise, like, you know, we've sort of done this benchmarking, and so we have an idea of the relative performance of different sorts of methods and when they tend to agree with one another and when they don't. And so, yeah, nothing that we've seen in this data has cast any doubt so far on this theory, the basic theory that we have behind our method Dowey. Okay. All right. So, okay, I won't talk about that. Okay, so yeah, all right. So we have an idea for a way of calculating hydrodynamics using a classical simulation of quantum many-body systems, which and this algorithm uses significantly fewer resources than existing brute force methods, and we are conjecturing that there's a nice sweet spot where you can significantly reduce the amount of memory you need, and therefore actually like practically get a useful estimate for diffusion constants. while at the same time, yeah, you make the calculation tractable, but you don't introduce too much error. And we have a basic theory for what kind of error you introduce for a given amount of memory. And our theory predicts this quite dramatically different predictions for how much memory you need for existing group forth methods and our methods, if you want your diffusion constant to look at this in the next slide. And I think one thing that we're really interested in doing is kind of getting into a kind of arms race with people who want to do these analog quantum simulations of many body systems. And why hopefully it's a win-win thing, because if we make our algorithm better and then that spurs them to find ways of getting rid of additional sources of decoherence in their experiments, that's good for everyone. And if their experimental improvements lead to us coming up with even better implementations of algorithms like these, then that's also useful. So yeah, anyway, that's what I wanted to say. Thanks.
Okay, so